Greeting. Class Math 200. Greeting, Professor Agu. I've made this video presentation to show a tree graph that I've made related to the Fibonacci sequence. And the Fibonacci sequence goes like this: 1, 1, 2, 3, 5. Now we can see the patterns here. To get to 2, we have to add the 2 previous numbers. 1 plus 1 gives you 2. Now to get to 3, we have to do 2 plus 1 to give you 3. To get to 5, we add the 2 previous numbers also. 3 plus 2, that gives you 5. So you can continue this process to get to any number of the Fibonacci sequence. To get to the following number after 5, all we have to do is to add 5 plus 3, that will give you 8. So the next number is going to be 8. So this process, following the same pattern, you can generate an infinite numbers of the Fibonacci sequence. Now I've made this graph here, as we can see, to represent the same phenomenon. And because Fibonacci sequence occurs in many natural processes, biological processes, naturally, such as in the growth of some flowers, and such as here in the family tree of the male honeybee. Now the male honeybees, they come from an unfertilized egg, meaning they have only one parent, their mother, so a female. Now the female of the honeybee family tree have 2 parents. They come from fertilized eggs, so they have 2 parents. So I have colored here the males in yellow and the females in green. So we can represent the family tree of a male honeybee like this. A single male comes from a single female, and that female comes from 2 parents, female and a male. Each female in the tree will have 2 parents, but each male will have only one parent, their mother. So, and each female will have 2 parents. So we can continue the same process. We will be exactly reproducing in each generation a number that's equivalent to the Fibonacci sequence number. So in the first generation, we're going to have 1, and the second generation, which is the parent generation, we're going to have only 1. The third generation, let's say that's the grandparent generation of the male family, the male honeybee, we will have 2 members. In the 4th generation of the male honeybee family tree, we will have that will be equal to the great grandparents. We will have 3 members. We will have 2 female and a male. So we can continue the same process. The ancestors, So this phenomenon occurring naturally, not just in the family tree of the male honeybee, as I mentioned earlier, it happened in flowers, in many other processes, is actually very interesting. So the ancient Romans, discovering this phenomenon, thought that this is a secret code of the universe that God himself implanted in the universe. So they use the same proportionality that you can find in this sequence to build, for instance, many construction, historical buildings that they constructed, monuments and stuff like that. So they maintain the proportions that you see in the Fibonacci sequence. Now, let's look at the proportion in the Fibonacci sequence. If you take 5 here and divide by the number preceding it, 3, you get 1.6. So if you continue further along in the sequence, if you take 8 and you divide 8 by 5, you get the same thing, 1.6. So if you continue in the process, along in the process, you're going to be generating number, almost, all of them very close to 1.618. That ratio is called golden ratio. So the ancient Roman used that ratio, for instance, in their construction. If they want to build, for instance, a structure with a rectangular shape, what they will do is represent the length of the rectangular shape, for instance, by a number of the Fibonacci sequence. Let's take 8. So they will do 8 meter long, for instance, and then the short side will be 5. So they will have the proportion of the golden ratio. So, and so this tree, which is a graph here, this graph is a tree. It will mimic the Fibonacci sequence, and we can see here I used 2 color scheme in this graph. So the chromatic number of this graph will be 2. You have many nodes here representing elements, so many vertices. Actually, up to the 5th member, we're going to have 12 vertices, and we have a connection between these members that are called edges. So we have 11 edges. There's actually one number less than the number of vertices each time in this representation. So let's say you have 25. I'm throwing out a number like that. Let's take 34, which is the member of the Fibonacci sequence. So if you get to 34 nodes, 34 vertices, you will have only 33 edges connecting them. So, making this graph, allow me to see that you can do such connection. Thank you, everyone. Thank you, class, and thank you, Professor Agiu. And I'll be making another one soon. Thank you.